In this video, we're going to talk about discrete and continuous random variables. When you think about the term random variable, it sounds like any variable in mathematics because it feels random. But in our purposes, we're talking about random in terms of probability, right? So randomly selecting a card or a person from a group. And a random variable takes numerical values that describe the outcomes of a chance process. So we use a variable to define all of the probabilities or a probability distribution of all the probabilities that could happen given the values of that random variable, right? Because the reason it's variable is that it can vary or change. So for example, let's say we toss a fair coin 3 times, and this is the sample space, right? You can get 3 heads in a row, you can get head, tails, heads, etc. And so let's say that we define our random variable x as the number of heads obtained in 3 tosses. So if x is the number of heads, it could be 0, where that's tails, no heads. 1, where you get 1 head, so head, tails, head, tails, or tails, heads. It could be 2, you get 2 heads and 1 tail in any combo of those. Or 3, you get all 3 heads. And so the probability distribution is something like this. So the value of x, if it's 0, that's 1 out of 8. If x is 1, that's 3/8. 2 is also 3/8, and then 3 is 1/8. A certain type of random variable is something we call a discrete random variable. And so that means that x, if that is your random variable, takes a fixed set of possible values with gaps between them. And if you were to think of a discrete graph, that would be like a scatter plot. You've got a bunch of points, but they're not connected by any curve or line. That's what makes it a discrete random variable or graph. And so we looked at something like this distribution, which was that tossing of a coin 3 times, and the x was the number of heads that you can get, so you can get 0, 1, 2, or 3. And so the deal with having discrete random variables are these 2 things. So every probability is a number between 0 and 1, inclusive, right? Because that's how probability works. And the sum of all the probabilities should add up to 1. And then this little note down here is be sure to consider whether or not you want to include a boundary value. So a boundary value is when, let's say you wanted to find the probability of getting at least 2 heads in that last example. So you have to consider whether or not you want to include 2, so like greater than or equal to, or if you just want to exclude 2, for example. So take that into account, as you would with all things. All right, let's do a 2-part example. So this one's called Apgar scores, baby's health at birth. So we're going to be talking about discrete random variables. In 1952, Dr. Virginia Apgar suggested 5 criteria for measuring a baby's health at birth. So skin color, heart rate, muscle tone, breathing, and response when stimulated. She developed a 0, 1, 2 scale to rate a newborn on each of the 5 criteria. And a baby's Apgar score is the sum of the ratings on each of the 5 scales, which gives a whole number value from 0 to 10. Those scores are still used today to evaluate the health of newborns. Although this procedure was later named for this doctor, the acronym APGAR also represents the 5 scales: appearance, pulse, grimace, activity, and respiration. So, what Apgar scores are typical? To find out, researchers recorded the scores of over 2 million newborn babies in a single year. So imagine selecting a newborn baby at random. That's our chance process. Define the random variable x as the Apgar score of a randomly selected newborn baby. And then this table gives the probability distribution of x. So we've got 0, we don't know what 0 is, 3 question marks. Remember, this is a sum of all of those categories, so appearance, pulse, etc. So if they only got a total of 1, that's 0.6%, 2 is 0.7%, etc., all the way down to 10, which is about 5.3% chance. So let's write the event. The baby has an Apgar score of 0 in terms of x, then find its probability. So how we write that probability is P of this x equals 0. I also forgot to mention that normally our random variable x is a capital x. It's okay if you wrote a lowercase, but we'd have x is equal to 0. And so in order to find this 3 question mark thing, I'm going to add up all of these probabilities and subtract it from 1, because remember, all these probabilities should add up to 1, or 100%. So adding up all these values, it's 0.999, and 1 minus 0.999 is 0.001. So that's the probability, about 0.1%, of getting a score of 0. Part B says, doctors decided that Apgar scores of 7 or higher indicate a healthy newborn baby. So let's find the probability that a randomly selected newborn baby is healthy. So this is that boundary situation where we have x is greater than or equal to 7, because a score of 7 or higher, so 7, 8, 9, or 10. So what I'm going to do is I'm going to add up the probabilities for 7, 8, 9, and 10 and figure out what's the probability of selecting a healthy newborn at random. So when I add up all 4 of these values for 7, 8, 9, and 10, I get 0.908, so 90.8%. So what can we do with discrete random variables and their probabilities? So we can graph them, of course, and we can analyze those graphs. And one thing that we can do is describe the shape of those graphs, which we did at the very beginning of the year. So, for example, if you were to make a bar graph or a histogram of the Apgar score from 0 to 10 and their probabilities, where the probability is on the y-axis, right? This was the chart we just had. And we can describe the shape of this. So definitely single peaked right here at 9 out of 10 score. And it is definitely skewed to the left, because remember, we look for that tail. Where's that tail? It's to the left. Another thing we can analyze in probability distributions is the mean, or the expected value of the average. So the mean, or expected value, of a discrete random variable is its average value over many, many repetitions of the same chance process. That shouldn't surprise you. That's been a very common theme. So suppose that this is our definition of our x, so our random variable, and then this is our probability distribution. To find the mean, this is technically the equation, but I prefer the words in this situation. So you multiply each possible value of x by its probability, and then you add all those products up. So let's work through that Apgar scores distribution and find the mean. So earlier we defined the random variable x to be the Apgar score of a randomly selected newborn baby. The table gives a probability distribution of x once again. So let's calculate and interpret the expected value of x. So what I'm going to do is I'm going to multiply 0 by this, 1 by this, 2 by this, etc., all the way up to 10 times this. I'm going to add all those values together, and that should give me my mean, or expected value, of this distribution. So we can call that capital E of x, so that's my expected value. You could always do the mean value here, a little mu of x, because that is our value of xi. And like I said, going to do 0 times 0.001, et cetera, up till 10. So let's figure out what that is. So the expected value, or the mean, is going to be around 8.128. And when we interpret that, one way to say is if many, like a lot of newborns are randomly selected, their average Apgar score will be around 8.128. So, average healthy babies. So we've talked about shape, we've talked about a measure of center, aka the mean, and now we're going to talk about variance, or standard deviation. Our good friend standard deviation is back. So the standard deviation of a discrete random variable measures how much the values of the variable, so that capital X, that first line here, how much that typically varies from the mean. So of course you have to find the mean, and the difference between the value minus the mean squared, right, because that's part of standard deviation, that's what we call the variance. So all of this is to say that we take that first x value, we subtract the mean, and we square it, and then we multiply it by the probability, and we add up all those terms, and now it's squared, and whatever that sum is, we take the square root, and that gives us the standard deviation of that discrete random variable. I have a feeling you knew where I was going with this. So we're gonna find and interpret the standard deviation of those lovely Apgar scores. So earlier we defined the random variable x to be the Apgar score of a randomly selected newborn baby. The table below gives the probability distribution of x once again. In the last example, we calculated the mean of a randomly chosen newborn baby. The mean Apgar score is 8.128. So let us calculate and interpret the standard deviation of this whole thing. So the first thing I'm going to do is I'm going to find variance. So that is that difference from each of these values minus the mean, 8.128, times its probability. So that's going to be the variance, which is squared, and we're going to take the square root of that value eventually. So how we set this up is 0 minus the mean times its probability. So 0 minus 8.128 times 0.001. Next term, 1 minus 8.128 times its probability, 0.006. Add up all of those same combos until we get to 10 minus 8.128 times its probability. So I compute all of that and I get 2.066. And so I take the square root of that value and I get 1.437. Number's great, but what does it mean? So that number, 1.437, tells us that any randomly selected newborn baby's Apgar score will typically vary from the mean of 8.128 by about 1.437 units. So that's the standard deviation of the Apgar score. So another type of random variable is something that we call a continuous random variable. And so how discrete and continuous graphs, for example, differ. Remember, discrete graphs are just dots, so like a scatter plot, and continuous is most functions you've seen in other math courses, right? So lines, curves, anything that is continuous, right? You put your pencil down, you trace it, you don't pick your pencil back up. That's a continuous function, or the graph of a continuous function. So a continuous random variable can take any value in an interval on the number line. So you're not beholden to value of 1, 2, 3. It can be any value from 1 to 2, for example. So 1.1, 1.121, whatever you want. So how we find the probability for a continuous random variable is a density curve. Remember those? That is just taking a rectangle and finding the area. So the probability of any event involving a continuous random variable is the area under a density curve and directly above the values on the horizontal axis that make up the event. So, for example, that density curve. All right, one last example, and we're leaving the newborn babies behind. Sorry, not sorry. We've actually talked about Selena before, and this one's called, Will It Be Quicker to Walk to Work? So, if you don't remember, Selena works at a bookstore in the Denver International Airport. She takes the airport train from the main terminal to get to work each day. The airport just opened a new walkway that would allow Selena to get from the main terminal to the bookstore where she works in 4 minutes. She wonders if it'll be faster to walk or take the train to work. So let capital Y equal Selena's journey time to work in minutes by train on a randomly selected day. The probability distribution of Y can be modeled by a uniform density curve on the interval from 2 to 5 minutes. So we'll find the probability that it'll be quicker for Selena to take the train rather than walk that day. So this is a continuous random variable because her commute can be anywhere from 2 to 5 minutes, any number between 2 and 5 in terms of time. So we start with creating a density curve, and remember that's just a big old rectangle. So on the x-axis is our y variable, slightly confusing, and that is Selena's journey time in minutes. So we have from 2 minutes to 5 minutes, because that is what the problem has asked us to do. But keep in mind that we will start at 2, but we end at 4 because we're talking about taking the train, and the train will get her there in 4 minutes. So it's from 2 to 4, and 4 minus 2 is 2. But that's not going to be our height. Remember, if it's from 2 to 5, the distance between 5 and 2 is 3. And what do we multiply by 3 to make it 1? 1/3. So we would draw this rectangle from 2 to 4 with a height of 1/3. So we're just going to find the area of that. Length times width. So 2 times 1/3 is 2/3. So the probability that y, which is Selena's journey time to work, is less than 4 minutes is 2/3, or about 66.7%. So what does that mean? There's a 66.7% chance that it will be quicker for Selena to take the train to work on any randomly selected day. So she should probably take the train. Probably. All right, that's going to do it for this video. Thanks so much for watching.